In modern data centers, the physical availability of rack space ultimately defines the absolute limit of computing density. Within a single 2U enclosure, manufacturers must integrate dual processors, 24 memory DIMMs, and a high-density disk array. This hardware sits within a metal chassis measuring just 3.5 inches in height. A dual-socket server acts as a decentralized network of high-speed hubs, coordinating data across independent domains. To understand the engineering of this node, we must look past the outer shell and map the internal high-speed data pathways. The system board block diagram serves as the foundational architectural blueprint for the hardware. The physical placement of every capacitor, slot, and chip is a direct manifestation of this logical map. High-bandwidth data routing via PCIe and memory channels dictates the absolute maximum length of copper traces to strictly maintain signal integrity. These electrical requirements are further constrained by the need for unidirectional airflow to dissipate heat from high-density silicon. Pulling the cover off the chassis reveals a motherboard packed with heat sinks and circuitry that reflects these constraints. Mapping the logical schematic directly onto the physical board demonstrates the engineering requirements behind the system topography. The architectural breakdown begins at the core processing units, identified here as CPU1 and CPU2. The Intel Quick Path Interconnect, or QPI, bridges these two processors. This bridge allows the CPUs to share workloads and access shared resources while operating as distinct domains. Each CPU acts as a hub for its own direct attached independent memory channels. On the physical motherboard, this corresponds to the two central heat sinks flanked by 24 DIMM slots. Immediate physical proximity between the DIMM slots and the CPUs is required to ensure ultra-low latency and signal integrity across the memory traces. The strict symmetry of this core layout is a byproduct of electrical trace impedance rather than visual design. Running dual CPUs and 24 DIMMs at high frequencies in a confined space produces significant heat as a byproduct. Effective cooling requires a constant stream of high-velocity, unidirectional airflow. To achieve this, the chassis contains a row of 6 redundant hot plug fan units positioned immediately behind the storage base. The placement of these fans forces air directly over the highest heat components before it is exhausted out the rear of the unit. Thermal exhaust requirements dictate the physical location of components just as rigidly as the limitations of electrical signals. The R720XD variant utilizes a storage footprint of 24 drives across the front of the chassis. When these drives operate simultaneously, they generate a massive concurrent input-output payload. The logical map shows how this data reaches the compute core through the internal PERC block. The Power Edge RAID controller, or PERC, is a specialized processor dedicated to storage management and parity calculations. The PERC interfaces directly with CPU1 through dedicated PCIe lanes. This offloads storage-related I/O from the primary memory and QPI buses, preventing storage operations from impacting general compute performance. Scaling to this storage density requires these distinct logic modifications to avoid creating a system-wide bottleneck. Below the high-speed data buses, the server manages lower-speed peripherals and legacy inputs. This traffic is handled by the South Branch, which isolates low-speed overhead from the primary CPUs. Branching from the South Bridge is the Integrated Dell Remote Access Controller, or iDRAC. The iDRAC functions as a completely independent, autonomous system on a chip. This logical independence is reflected in the physical rear panel, which features a dedicated network port for out-of-band management. This dedicated path allows for hardware-level telemetry and power cycling even if the primary operating system is unresponsive. Because of this logical segregation, the management layer operates independently of the host's primary processors. An enterprise server is a nested architecture of specialized brains, each requiring its own dedicated data paths and physical I/O. We can now finalize the connection between the abstract block diagram and the physical chassis. Viewed in its entirety, the internal topography of the R720 follows the logic of the system schematic. Superimposing the logical blocks from the schematic shows their direct correlation to the physical motherboard components. The groupings of capacitors and slots align with the high-speed pathways for QPI, memory, and PCIe data. The enterprise chassis is a physical extrusion of its logical architecture and its thermal requirements. To analyze a motherboard is to see the functional intent behind the placement of every component.
The layout provides a map of data flow, latency limits, and thermal topography. Understanding the relationship between schematic logic and physical constraints explains how a server maintains high availability under load.